This lesson is on 6.5, trapezoidal rule. So as you can see, we are now hitting a new type of geometry to help us figure out approximations of areas under the curve. Now again, these rules, the rectangles or trapezoids, these are all approximations. And while calculus, the fundamental theorem of calculus, allows us to figure out the exact value of the area under the curve, sometimes we're not able to do that. Sometimes we're given only data points, and then so we have to figure out what is the best way to approximate. So we know that calculus gives us the exact value. That's why we're able to use formulas and functions and use those, treat those as approximations, and then you're able to compare and say, okay, well, because we know what the final answer should be, because we know the exact value from using calculus, then we can go back and compare and say, hey, is LRAM better? Is RM better? Is MRAM better? Is trapezoidal rule better, right? So that's why in our examples, we always use it where we have a function. But again, ideally, realistically, all these approximations should be used when you don't have a function, when you're given data points and you're asked to approximate without an actual function. These approximations actually get you a very good start towards what you really want, okay? All right, in the beginning, we're just gonna remind you again of how to combine integrals into one. Remember, integrals are areas under a curve, right? So can you combine area? And the answer is yes. So you've done a few of these in your in your worksheet. And the key is when you're combining the integrals, the best way to look at this is to have the b of the first integral match the a of the second integral. Meaning you have a beginning to end, and then you have another beginning to end. You want the end and the beginning of these two to match up so you can get rid of that middleman. So what am I talking about visually? Visually, what I'm trying to say is here is your x and y axis, right? If here's my function, because it has to be the same function, that's f of x, right? And I tell you that the first piece is from A to B, so that's the first piece. And I said, okay, here's a second piece that goes from B to C. If I want you to combine those two, you simply take away the B in the middle, and you say it's really from A to C, right? So you want the end, the B, to match the beginning, the B, of the second one, right? You want to match those two, you want those two numbers to match, okay? So in terms of integral, what does that look like? In terms of integral, you want A to B, f of x to match the B to C. You want these two numbers to match up, right? Because then you can say, okay, really it's really A to C. I don't need that B in the middle, okay? So even if you don't know what the shape looks like, you can look at the integral and say, okay, well, based on that fact, the shoe says A to B and then B to, so the numbers have to match. So the first thing you look at this problem is, oh, I do see a number that they both have. They both have 4s, but the 4 is in the wrong place. We want the 4 to be up here and the 4 to be down here, and then we can combine them, right? We can get rid of them. So remember how we could switch integrals? We can switch the interval numbers by adding a negative in front. So if I put a negative in front, so here's my work here, put a negative in front, this now becomes 1 to 4, f of x dx. And then put negative in front, this is now 4 to 6, f of x dx. All right. Remember, this is an area, right? So these are numbers. So you can actually look at this and say, well, there's two negatives there. I can actually factor out a negative. So it's negative integral 1 to 4, f of x dx, plus, because you factor out a negative, 4 to 6, f of x dx. And now I have the numbers matching in the right places. The 4's go away. So now I have this final answer of 1 to 6, f of x dx. Now, some books don't like that answer because they don't want the negative in front. So remember, what the negative does for us is to flip the interval. So really, you could write your final answer as 6 to 1, f of x dx. And that would be a good final answer, okay? If you want to keep the answer the set before, that's totally fine. Again, it's just reminding you that when you're seeing this on a multiple choice, you want to know that both of them are okay. All right. Okay, so next piece, I have negative 2 to 6, and then minus negative 2 to 2. Okay, so first things first, what is the number they both have in common? Oh, I see, it's a negative 2. So are they in the right places? Well, this one is, because that negative 2 is on the bottom, and then the other one, negative 2, is not. So I need that on top, so I'm going to do the same trick as before. Apply a negative, and put negative 2 on top. f of x dx minus negative 2 f of x dx. And same thing, you notice that they both have a negative, factor that out. So factor out a negative, you have 6 to the negative 2 f of x dx plus negative 2 to 2 f of x dx. And since they're in the right places, now that negative 2's are gone, and you can rewrite this as a final 1 integral of 6 to 2 f of x dx. And the negative allows us to write it as 2 to 6 f of x dx. All right. Now again, that flipping may make it better. Like in this case, we have now from small to big. That's actually what we really want. Whereas number 1 has it from big to small, and it's okay. It's okay to have that kind of reverse order, and it'll make a lot more sense once we start doing our FRQs. Why the reverse order sometimes is actually helpful to our cause. Okay. All right. Next one, I see that, I want m and m because those are the only two numbers that match, right? Well, the first m is in the right place, the second one isn't. So to move the m to the bottom, I need to add a negative to it. So now this looks like c to m, f of x dx. Add a negative, it's already a negative here. This becomes plus m to d, f of x dx. And then the beautiful thing is m's go away, leaving you with just integral c to d, f of x dx. Right, and you're done. You don't need to switch to c or d. You don't know what values are, so you don't know if one's bigger, one's smaller, so you leave it as is, okay? And also, don't make the assumption that because c alphabetically is in front of d, that c has to be a smaller number than d. That's not necessarily the case, okay? All right, so let's move on to the trapezoid rule, right? So that was just kind of a reminder of what we were doing, and I think your homework does have a little bit more of this practice, so make sure you are comfortable with this type of, arbitrary fake function problems where you're just combining your areas or subtracting your areas. Okay, so there is a trapezoid rule, meaning that there is a way to simplify your way of multiplying or adding up all the trapezoids, just like LRAM, RM, MRAM. If your width is all uniform, if your width is all the same, then our formula makes it easier that we have the width on the outside and we just add up all the heights, right? So same thing. If you recall one single trapezoid, right? One single trapezoid is 1/2 base 1 plus base 2 times height, right? So I see the height and the 1/2. If I combine the height and the 1/2, it's right here, the height over 2, okay? Now, what's all this y0, y1, y2, y whatever, right? So think about what this is saying. Trapezoid rule says, and I'm just going to try to draw a picture to show you without getting too much into the problem. Now I'm going to use this blank space on the side here. Okay, so I'm going to erase this because I want to use some space here. Okay, so what does it look like? So here's my x and y axis, and typically, I do a little quadrant 1. You could do this over any quadrant. It's just quadrant 1 is a little bit easier to talk about. Okay, so here is my function, right? And here is the area I want you to look at. Okay, and then I say divide this up into however many rectangles or trapezoids. So I'm going to divide this up into trapezoids, right? Just a few. And they have to be, all right, so sorry. They pretend they are equal length, all right? But the key thing is, look at this. If I'm trapezoid, what do you mean, Miss Chu, trapezoid? If you connect it like so and turn your head sideways, this is a trapezoid, right? These are the parallel sides, and so it's a trapezoid going this way, right? And so if you connect all your endpoints like so, notice how my trapezoid is actually a much better approximation. Notice how the gap is so much smaller, right? And again, we'll see that in action in the next two problems, but this is the idea of it. Now, think about this. In the first trapezoid, here's my base 1 and base 2. In the second trapezoid, this is my base 1, base 2. Next trapezoid, base 1, base 2, base 1, base 2, base 1, base 2, base 1, base 2. So you notice how that all of your in-between bases, all your in-between heights, y values got used twice, but then the first one got used once, and the last one got used once. So because of the formula, it has to have base 1 plus base 2, base 1 plus base 2. Those numbers got used twice, and hence the formula. The first y value is by itself, the last y value is by itself. But all the y values in between got doubled because of the fact that it has to be doubled, because the base 2 of the first now becomes a base 1 of the second, right? And then so on and so forth. So this is why the formula has those 2's and the non-2's. Okay. Now, if I want to know the height, and again, we use the word height kind of loosely. Height is this one right here. It's our width from before. So the height is b minus a over n. We talked about this. It's the endpoints subtracting each other and divided by how many trapezoids we have. Right. Now, equivalently, this is kind of cool. A lot of kids say, oh, well, you have LRAM and RRAM and you have MRAM. Since MRAM is the midpoint, don't you just take LRAM, RRAM and average it out? No, actually, when you average out the LRAM and RRAM, it becomes trapezoid. So that's a check for yourself. If you only have data points and you are asked to define LRAM, RRAM, and trapezoid rule, once you use the rules to find those, you can actually use the answers to check and see if each other is correct. So that's something in the next lesson that we'll talk about. Okay. All right. So in the direction says, in these problems, both problems, I use a trapezoid rule with n equals 4 to approximate the integral. In part B, use the concavity of the function to predict whether the approximation is an overestimate or an underestimate. And then find the integral's exact value. So we're going to see how good our trapezoid rule is. Okay. First step, we want to draw this picture, right? So the function is x squared plus 1. What does x squared plus 1 look like? Well, x squared plus 1 is a parabola. It's up 1, and then it curves out. So 1 squared is 1, 2 squared is 4. And because this is a parabola, I'm going to curve up like so, right? Now, notice how Miss Chu only did it from 0 to 2 because the interval is 0 to 2. All right, so make sure you do that. Then it says n equals 4. What that means is you want 4 trapezoids. So you want to go kind of zoom in a little bit and see that, okay, your regions from 0 to 2, you can figure out how wide to make your trapezoid by following formula. The height of your trapezoid, the width of your trapezoid is 2 minus 0, that's b minus a, over n. So that's 2 over 4, that's 1/2. That means then halfway at 1/2, that's where I'm going to draw my trapezoid. If you see the markings there, you will notice that once you mark every half, you have 4 intervals, and thus it will make your 4 trapezoids. Okay? And then the trick is to go up until you hit the function. So I'm just going to draw my line until I hit the function. Right? Draw all the way up until I hit the function, and then hit the function. And then you connect the endpoints. Connect your endpoints. Connect your endpoints. And connect your endpoints. So it's really hard to see, but hopefully the last one you see as I zoom in here, you see when your concavity is concaving up, your trapezoid is going to be an overestimate. In fact, if you want to, just draw like a very exaggerated example for yourself. If it's concaving up, here are your 2 endpoints. To connect those and make your trapezoid, you will always be overestimating. Even if it's on the other side, you have these 2 lines and then connect, you see you are overestimating. So a concaving up will always be overestimating. Okay? All right, so let's answer the question first. Let's see. It says we're going to use the trapezoid rule. So how does that look when it's in action? So part A, what you want to do is you want to do the same thing as before. You want to create a t-table with the values that you see on your graph here. What values am I talking about? I want to see the y values of 0, 1/2, 1, 3/2, and 2, right? So all those y values that we see there. All right, plug into my formula. 0 squared plus 1 is 1. Okay. 1/2 squared is 1/4. 1/4 plus 1 is 5/4. 1 squared is 1 plus 1 is 2. 3/2 squared is 9 over 4. 9 over 4 plus 1 is 13 over 4. And 2 squared is 4. 4 plus 1 is 5. So those are your values. Okay? All right. Formula says, trapezoid rule says, T sub 4. T sub 4 means 4 trapezoids. T sub 5 means 5 trapezoids. So however many trapezoids you have, that's the number you put underneath. Okay? Equals the height, which we got. The height was 1/2. So 1/2. Don't forget over 2, because that's a formula, right? And then y naught, meaning the first y value. The first y value is 1 plus 2 times the next y value, 5 over 4, plus 2 times the next y value, 2, plus 2 times the next y value, 13 over 4, and then plus a single 5. Okay, remember, only the first and the last don't get doubled. Everybody else get doubled. Okay. All right, so I get 1/4, because 1/2 divided by 2 is 1/4. You have 1 plus 5 over 2 plus 4 plus 13 over 2 plus 5. So I'm going to add up all my numbers here. So 1 plus 4 plus 5, that's 10. 5 plus 13, that's 18. 18 over 2 is 9. So I get 19 over 4. That's my approximation, 19 over 4. Which again, for me personally, 19 over 4 is a little hard to compare, so it may be helpful to put it in decimal form. So if you divide it by 4, divide it through, you get 4.75, right? So hopefully that will help us figure out the approximation, how good our approximation is next, all right? Next, we have using the concavity. So you want to prove your concavity by taking the second derivative. So f of x is equal to x squared plus 1. So to find concavity, recall your memory from back to chapters 3 and 4. So f prime is 2x, f double prime is, oops, sorry, all these weird numbers. F double prime is 2. 2, there's no x. 2 is always positive, so therefore this is always going to concave up. Now we drew our exaggeration. You might want to do it again right here. If it concaves up, no matter which way you are at, right, whether you're on the left side or on the right side, you see you are always going to overestimate. So because it concaves up, oops, up. This is an overestimate. Okay, so that means our answer should be bigger than my integral. All right, so let's see. That's what part C is. Part C says, actually figure this out. Figure out your integral and see what you get. So integral from 0 to 2, x squared plus 1 dx. Okay, so I'm going to take the antiderivative. That's x cubed over 3 plus x, evaluated from 0 to 2. Plug in your 2, you get 8 over 3 plus 2 minus 0 over 3 is 0 plus 0. Awesome, I love zeros. So you get 8 over 3 plus 2. That's 8 over 3 plus 6 over 3, 14 over 3. Okay, now you want to figure this out. 14 over 3, if I divide it through, that is about 4.6666, so 4.67, right? How is that compared to my approximation? My approximation was 4.75. My actual value is 4.67. Not bad at all, right? Again, I usually use money to compare. I'm off by 8 cents. That's not so bad, okay? All right, so trapezoid rule is actually a really, really good rule in comparison to LRAM, RM, MRAM, all right? So trapezoid is actually one of the better ones, okay? All right, well, you probably guessed it. We did a concaving up, so we're probably gonna look at a concaving down, right? So let's see what this function looks like. So the next function is a cube root of x, right? So if you recall, cube root of x, the cube root of 0 is 0, cube root of 1 is 1, cube root of 8 is 2. Oops, it's missing a line, but you probably can guess there's a line there. Just so that it doesn't bother me, I'm gonna put a line in there. There you go. All right, beautiful. All right, so here is my function. Here is my cube curve. I'm sure there's more to the curve, but I only want it up to 2, right? That's what it says, 0 to 8, not 0 to 2. I only want it up to y equals 2, so 0 to 8. We still want 4 trapezoids. So just like before, we want 4 trapezoids. So you can figure out the height by taking 8 minus 0 all over 4. That gives me 2. That means 2, every 2 I can mark my trapezoid, right? So here is 1, 2, 3, 4. Okay, same as before, go up to your function, go up to the function, up to the function, up to the function, and then connect your endpoints. And again, as you can see, when your graph is slanted, the trapezoid actually looks really good, right? It's when it's exaggerated like this one, you can see, wow, trapezoid is actually an underestimate, right? So you can draw the same picture you did for yourself before and see that really, when you're curving like this, an exaggeration would be find these 2 endpoints and then connect them and see that it's always going to be an underestimate. Okay. All right. So how do I do part A? How do I do a trapezoid rule with this? Well, I'm going to make my t-table as before. So x, y, and keep in mind, I am going to have the same intervals as before. So my height is 2. So it goes 0, 2, 4, 6, 8. Okay. So now the function is cube root. So cube root of 0 is 0. Cube root of 8 is 2. And just since it's an approximation, it actually is okay to grab a calculator and figure out the cube root of, because otherwise there's no point leaving it as cube root of 2. If you leave it as cube root of 2, it doesn't help you figure out what the approximation is, right? So take your calculator out and go, all right, cube root of 2 is about 1.259, so 1.260. Okay. Cube root of 4 is about 1.587, and then cube root of 6 is roughly 1.817. Okay, all right, now I'm ready to find the trapezoid rule of this. So the formula says take your height was 2 over 2, that's a formula, height over 2, times the first value 0, second y value double, so 2 times 1.26 plus 2 times 1.587 plus 2 times 1.817 plus 2. Okay, that gives me 1. And then 1.26, you double that, you get 2.52. 1.587 times 2, I get 3.174. And then 1.817 times 2, I get 3.634 plus 2. So that gives me, oops, I don't need that parentheses anymore. All right, so if I add them all up, I get 3.174, I add 2.52, I add 2, I get 11.328. Okay, so that's my approximation. Right, remember we had to round, so I'm sure my answer later will have to round a little bit too. Okay, all right, so then we use concavity, and we already kind of discussed what the concavity of this is. This is concaving down, but we're going to prove that by finding our derivative, right, back from chapter 2, chapter 3 and 4. So your f of x is x at 1/3, it's cube root, right? So f prime is 1/3 x to negative 2/3. F double prime is equal to negative 2/9 x to negative 5/3. All right, so what that looks like is really negative 2 over 9 x to 5/3. Okay, so in this particular function, it's not as easy as the previous one where it's just a single number and we can see that it's concaving up constantly. In this case, depending on your x, right? If your x is positive, you're taking it to a fifth root and a fifth power, and then cube root it, it's still going to be positive. But because of the negative 2 on top, it's going to make it negative. So when your x value is positive, you're concaving down. But if your x value is negative, you plug a negative number in there, fifth power is still going to be negative, cube root that is still going to be negative, but then you have the negative 2 on top, so making it positive. So because our interval is from 0 to 8, so interval is 0 to 8, therefore it only concaves down because it is going to be negative, right? And because it concaves down, it's going to be an underestimate. Okay, so it means my estimation from part A is lower than my actual value, so I should get a number bigger than 11.328. Okay, now it's a test of our integral skills, right? So part C, you're actually going to find 0 to 8, cube root, so instead of writing cube root, I write x to 1/3 because we changed it to a power rule. Okay, and derivative says x to the add 1, so 4/3. Now multiply by reciprocal times 3/4, 0 to 8. Okay, so that is 3/4. Instead of plugging in 8, I'm going to plug in 2/3, so that's easier to figure out the 4/3 out here. Minus 3/4 times 0 to the 4/3. This is why I'm hoping you remember why I like zeros, because typically when you plug in 0, everything's gone, right? Okay, so you have 3/4, 2 to the 3rd, 2 to the so those cancel out or reduce out, so you get 2 to the 4th. 2 to the 4th is 16. So that reduces out again. That reduces to 4. My answer is actually really nice. It's 12, right? So remember, we said my estimation was a little bit lower than my actual answer. All right, so we're farther off this time, and you can tell that because based on the picture, right? See how this portion right here, we have a huge, right here, we have a huge piece that we didn't take into account. But even so, we're off by, again, using number to look at this, using money to look at this, we're off by 60 cents, right? So it's really, again, not bad, okay? So Hopefully this gives you a good idea of how trapezoidal rule works, how to use the trapezoid rule. You could always definitely go back and check and see if your LM, RM, the average of it is actually equal to your trapezoid rule. But that is definitely more work. So I would say just get comfortable with this formula. It's actually not a bad formula, and get comfortable with it to know how to use this. Okay? All right, that's it, guys.